This graph represents the temperature of a water sample as it is heated for a period of time. The water begins below zero. Being below its freezing point, the water would be a solid at this point. Once the sample reaches the water's melting point temperature, or 0 degrees Celsius, the ice will begin to melt into a liquid. Both solid and liquid phases are present during the time it takes for the solid water to transition completely to liquid water. Once the phase change is complete, continuing to add heat will cause the temperature of the liquid water to increase. At 100 degrees Celsius, the water has reached its normal boiling point. While boiling, both liquid water and evaporated water in the form of gas bubbles will be present. Once all the liquid has evaporated into a gas and the phase change is complete, continuing to add heat will cause the temperature of the water vapor or the evaporated gas to increase. Now that we know what each segment of the graph represents, let's go back to the beginning and look at it from another angle. In this first segment, we can see the temperature is increasing from negative 100 degrees to 0 degrees Celsius. If we remember that temperature is a measure of the average kinetic energy, that means the kinetic energy is also increasing. Since kinetic energy is the energy of motion, we know the movement of the molecules is increasing in this segment, or put it another way, the speed of the molecules is increasing. The slope also increases between 0 and 100 degrees. Therefore, across this segment, the kinetic energy or speed of the molecules is increasing as well. This same trend repeats a third time in the segment from 100 to 200 degrees. In these three highlighted segments, only one phase of water is present, either 100% solid, 100% liquid, or 100% gas. But you'll notice while the water is transitioning from solid to liquid or melting, the temperature remains constant. That means the kinetic energy remains the same, represented here with the shorthand RTS for remains the same. If the kinetic energy is not changing, then the speed of the molecules is also remaining constant during this phase change. The same holds true at 100 degrees Celsius while the water is boiling. This demonstrates an important concept, and that is temperature remains the same during a phase change. That holds true whether the phase change is from a solid to a liquid or from a liquid to a gas. The temperature will remain constant during all phase changes. Why would the temperature stay the same? If the substance is still being heated, shouldn't we expect the temperature of the substance to continually increase? Why isn't this added energy making the molecules move faster? Well, changing from a solid to a liquid or a liquid to a gas requires the molecules to rearrange. When trying to move the molecules farther apart, there is an attraction or an intermolecular force between the molecules. These could be London dispersion forces, dipole-dipole attractions, or hydrogen bonds. This intermolecular force works to keep the molecules close to each other and must be broken for the molecules to change their spacing into a new phase. During a phase change, added energy is used to overcome the intermolecular forces to rearrange the particles, not to make them move faster. During melting, the temperature remains constant because the added heat is used to overcome the intermolecular forces so the phase change can occur. In the case of water, those intermolecular forces are hydrogen bonds between one water molecule and another. While water is boiling, the temperature will again remain the same because the heat is being used to overcome the intermolecular force so that the phase change can occur. Therefore, it's easy to identify where phase changes are occurring on a heating curve because the temperature will plateau or flatline during all phase changes. Let's see if you can apply these concepts to a graph representing a substance being cooled rather than heated. I'll get you started with the water vapor starting at 200 degrees Celsius. Now you sketch the remainder of the graph to end at negative 100 degrees Celsius. Be sure to label the phases present at each segment of the graph. Pause the video while you work and start again when you're ready. At 100 degrees Celsius, the line will plateau and remain the same during the phase change while the particles rearrange. However, since we're cooling the water or removing energy, it will be changing from a gas to a liquid or condensing, rather than boiling like it was in the heating curve graph. During this and all phase changes, the temperature of the substance will remain constant. Once the water is 100% liquid, the temperature will begin to decrease again as energy is continually removed. At 0 degrees Celsius, the temperature will plateau as the water freezes. Once the water is 100% solid, the temperature will begin to drop again as the water is further cooled. Thanks so much for joining me today. Remember, the key takeaway from this lesson is the temperature of a substance remains the same during all phase changes.